Now, let's move to parallel lines and perpendicular lines. Parallel lines are two or more lines that have the same inclination or slope. And therefore, whether two or more lines are parallel can be determined by finding their slopes. Let's look at the figure. Line 1 has a slope of m1 and line 2 has a slope of m2. If line 1 and line 2 are parallel, m1 is equal to m2 and vice versa. If m1 and m2 are found to be equal, we can tell that line 1 is parallel to line 2. And therefore, for any lines that are parallel to x-axis, it will be horizontal, and therefore the slope of the line will be 0. M for that line is 0. On the other hand, if there is a line that is parallel to the y-axis, which is completely vertical, then the line's slope is undefined. Now, let's talk about perpendicular lines. We all learned about transformation. If there is a point P with coordinates A, B, rotated anti-clockwise about the origin O through 90 degrees to point P' on a rectangular coordinate plane, the coordinates of point P' are negative B, A. If we look into the figure, line OA has a slope A over B. It is also the hypotenuse of right angle triangle AOB. When we translate triangle AOB about the origin O anti-clockwise through 90 degrees, it will get A prime O B prime. The slope of the hypotenuse of the triangle A prime O B prime is B over negative A. Hereby, the product of slope of OA and OA prime is A over B multiplied by B over negative A, and that equals negative 1. The converse applies. If the product of slopes of two lines is negative 1, we can tell that the two lines are perpendicular. Let's refer to this figure. The slope of L2 is determined using 2 points lying on L2 with the slope formula. Here we get negative 1. Considering that L1 is perpendicular to L2, the slope of L1 can be determined by the slope of L1 multiplied by the slope of L2 equals negative 1. And hereby we get 1 as the slope of L1. Conversely, if we get both slopes of L1 and the slope of L2, we could determine whether they are perpendicular. The product of slope L1 and slope of L2 equals to negative 1. And therefore, L1 and L2 are perpendicular. Now, we are going to talk about how the mathematical concept of slopes and Pythagoras' theorem could be applied in studying Chinese mitten crabs. First, I would like to tell you a little bit about the behavior of Chinese mitten crabs. Apart from migration, burrowing activities is another significant behavior of Chinese mitten crabs. Burrowing is to create a hole or tunnel into the ground by animals to make a suitable environment for habitation. Meaning, the crabs will dig a hole and live inside the hole. Burrowing behavior is common among crustaceans, such as crabs, lobsters, shrimps, etc. Regarding Chinese mitten crabs, while the tunnels mostly slope downwards from its surface of opening and lead to chambers where the crabs use for hibernation, there is always standing water in the chambers, or the soil surrounding the burrow is saturated with water. Burrowing protects the animals from environmental stress, such as dehydration and temperature extremes. Its function as a defense system against predators. Burrowing is also carried out by juveniles in Chinese mitten crabs. The shape and structure of burrows varies among species. Those of Chinese mitten crabs ranges from a single tunnel leading to a single chamber to complex burrows with multiple surface openings and bifurcation tunnels leading to multiple chambers. Burrowing is known to take place in soft sediment banks of intertidal portions, meaning the area between high and low tide lines. This picture shows the surface of openings of the burrows. Some scientists suggest a correlation between the density of the burrows and angle of the bank. Let's look at this drawing. The green line represents the high tide line, and the blue line represents the low tide line. Bank height means the vertical distance between high and low tide lines. Here, theta is the bank angle. While it is found that burrowing did take place at flat areas, there was a slight positive relationship between the burrowing density and the bank angle within a certain range. That means within a certain range of the slope, the steeper the bank is, the more favorable it is to the crab's burrowing. Now, let's go into another question. If you get the bank height and the bank angle, would you be able to find out the horizontal distance between a particular point to the water from the stream? Of course, we could simply make use of slope of the bank and Pythagoras theorem. We'll work this out later. As stated, the angle of the bank has a weak positive relationship with burrowing density of Chinese mitten crabs. Whether an area is ideal or at least suitable for general crab burrowing depends on a mix of factors. That includes sediment grain size, sediment composition, and proximity to water that may affect the water content inside the sediment. As shown in the figure, the burrow might be deep underground. To calculate the depth of the burrow, the length of the burrow tunnel and the angle of the tunnel gradients were measured. For example, gradients of tunnels made by a type of crabs ranged from 55 degrees to 85 degrees. The vertical depth of the burrow would be sine 55 multiplied by the length of the burrow tunnel to sine 85 multiplied by the length of the burrow tunnel. This simple calculation is for simple single straight burrow tunnels. For those with complex tunnel systems, more complicated calculations should be applied. The depth of the burrow is sometimes used to estimate the groundwater elevation, temperature, and moisture. We mentioned that the proximity to water is one of the factors in the sustainability for burrowing. When scientists get to study water content of sediment along with their distance from the shoreline as well as the groundwater elevation, they need to collect samples from particular points in the underground space. For example, we can regard this as the hypotenuse of a right-angled triangle. The site for the sample collection along the hypotenuse, AB, is points of 50 meters, 20 meters, and 25 meters from point A, the shoreline. And they collected sediment samples at 10 cm intervals along the vertical lines of each of these 3 points. You may have guessed right already. With particular horizontal distances from the shoreline, water content increased along with depth. Now, let's call the distance between sites for sample collection and shoreline X. We keep digging until we reach a stable water level, which is the groundwater elevation, and we call the depth of the surface to groundwater elevation Z. With X and Z measure, we could calculate the horizontal distance. Let's call it D between the sample collection sites and the shoreline using Pythagoras theorem. And the distance between the water from the shoreline and individual points of sample collection are actually the hypotenuse of right-angled triangles with a leg of D, another leg of Z minus depth of surface of collection sites. We could also find it out using Pythagoras theorem. Water content in the sediment is negatively affected by their distance from the shoreline water. But of course, besides this, water content in sediment is affected by the distance from the groundwater elevation as well. Water content increased with depth that negatively affected burrow depth. Crabs construct burrow tunnels in sediments within a wide range of water content. Perhaps it is an advantage when living under environmental fluctuations such as tidal cycles and precipitation events over time. Thank you for watching this video. If you enjoyed it, please do not forget to subscribe to our channel and give us a thumbs up. Looking forward to seeing you again soon.